Welcome to section 1.1. As we begin our journey through calculus, we're going to be starting off with some review of some algebra topics, just to kind of ease us into this. We're going to be starting off in section 1 talking about the idea of a function and relations, and see kind of how we relate variables to one another. So a function is defined as a rule that pairs each element in one set called the domain with exactly one element from a second set called the range. Okay, so we have one set of values over here. This is our domain, which is often abbreviated D. We have another set of values that we call the range, which is often abbreviated with an R. And then we have our function rule that goes between the two of them. So the idea is we're taking some element, some number, some value, whatever it may be, from the domain. We run it through the function. Okay, so we apply whatever this rule is to that value, and it changes the value into something that is over here in the range. Okay, so when we're talking about domain and range in context of the function, the domain is going to be the set of all possible inputs, and the range is the set of all possible outputs. So we take an input value, we run it through the function, okay, we apply the rule to it, and we get an output value that is in the range. So we can represent functions in several different ways. I think the most common way that we're experienced with is with formulas, right? What you study in algebra, algebraic formulas, f of x, that sort of thing. And we'll get to that. But we're going to start off with a couple other ways of looking at functions first. The first would be something graphical. Okay. So a ball is tossed into the air where its height is given by the function h equals 32t minus 16t squared for t going from 0 to 2, where h is the height in feet and t is the time in seconds. Construct a table that gives the height of the ball at quarter-second intervals, and then graph the function. So we have a few different ways that we're going to be looking at this one. We're going to be using this formula to construct a table, and we're going to be using the table to construct a graph. Okay, so a few different ways that we can view a function. I already have the values set up here for us. So we're doing this in quarter-second intervals from 0 up to 2. So when we go to find a value, we take the input, in this case that's the time or the t value, we run it through the function and get out an element of the range, which in this case is the height. So for example, for 0, we would have, when t is 0, h is going to be 32 times 0 minus 16 times 0 squared, which is also just 0. If we took, say, 0.25, so the next value, we run that through this function, okay, apply that rule, right, to this value, the input of 0.25. We get out of this the value 7. and then et cetera, et cetera. We continue on with this process. We can input all of these into the function and get out their corresponding outputs. So for 0.5, we get out 12. For 0.75, we get 15. 1 gives us a 16. Then a 15, a 12, a 7, and a 0. Okay, so what we have over here, again, the time. This is our domain, so this is our inputs. And then the height is our range, which contains our outputs. Because if I tell you how much time has passed since the ball was tossed, we could then figure out what the height of the ball is at that time. So let's go ahead and set this up here. So we're going to have our quarter-second intervals down here. .25, 1.5, 1.75, and 2. So these are all our t values, our times in seconds. And then for the heights, I'm going to count up by 2s here, since these numbers go as high as 16. Just save a little space. So from here, now, we take the time is 0, so that's right here, and the height is 0. So we plot a point. Then we go to a time of 0.25 right here, and we get a height of 7 right here. So that's going to be a point right there. And then 0.5 gives us 12. 0.75 gives us 15. 1 gives us 16. 1.25 gives us 15. 1.5 gives us 12. So you can see kind of the symmetry here. We're getting the same values on the left side and the right side here, and then back down to 0. And then we will connect the dots as smoothly as we can, reasonably. Don't just draw straight lines between everything, because it does have a curve. But obviously this isn't an art class, so it looks something like that. So this is the graph that represents this table, which represents that formula, all of which describe that function, okay, or that rule that is being established, that as time passes, the height of the ball goes up until it hits its peak up here, or the vertex, if you want to think about this in its parabolic form, and then it comes back down again. That rule is now established here in 3 different ways, and each of them give us kind of different aspects of the information. Now, let's look at functions in another way. Here we have a set of points. So these points, right, these are all coordinates x, y, like that. So we know how to plot points on a graph. What I want to do is I want to break this into domain and range. So we're going to take all of the input values, the x values. Those are going to be the elements of the domain. So we have 1, 7, 3, -1, 5. We already have a 1 and then a 10. And now for the range, we go to the outputs. So to the y's, that's 3, 2, 6, 8, 3, 4, negative 2. So get 3, 2, 6, 8. 3 we already have. 4 and negative 2. And now let's see what corresponds to what. So we have the 0.13. So 1 goes to 3, right? As the function gets applied, we take that input, it results in that output. 7 goes to 2. 3 goes to 6. Negative 1 goes to 8. 5 goes to 3. So that's also going to be up here. 1 goes to 4. So this 1 is also going to split here. And then 10 goes to negative 2. Now, in order for this set of points to represent a function, the rule of the function must pair each element in one set called the domain with exactly one element from a second set. And this key here is that it must be exactly one element. So when we look at the results, the first thing that I notice is this value of 1. It goes to 3, and it also comes down here and goes to 4. Right? 1 gets paired up with 3, but 1 also gets paired up with 4. This means that we have one input that has 2 different outputs for it. And that relationship means that this cannot possibly be a function. So we're going to say this is not a function because one input, the number 1, has more than one output. And that was 3 and 4. Okay, so those 2 points create a problem because we have one input going to 2 different outputs, and that cannot result in a functional relationship. One thing I do want to point out here, because this is usually a question that comes up, is the fact that both 1 and 5 go to 3. And I want to make it clear that different inputs can go to the same output. That's not really a problem. The problem is if one input is getting split into 2 different outputs. So just as a side note down here, so note two different inputs can have the same output. So 1, 3 and 5, 3. So that's not really a problem. The problem here is the 0.13 and 1,4. Now, we can also visualize this idea by looking some more at graphs. And specifically, we have one kind of rule, or I guess a test that we use, and that is the vertical line test. We use the vertical line test to determine if a graph represents a function. The relation will only be a function if every possible vertical line drawn through the graph will only cross the curve once. So let's take a look at a few functions. So we have here like the reciprocal function. So y equals 1 over x. So that's going to be, so we get like 1, 1, 1 half 2, 1/3 3, okay, 2 1/2, 3 1/3, etc. So it's going to be something like this. And it also has a negative branch. It's going to be down here. So this is roughly what that graph looks like. Now, in order to determine if this is a function, we look at any vertical lines that we could draw through this. And we see that no matter where we draw these vertical lines, we're only hitting 1 point at a time, right? And the only issue would be if these two pieces like overlapped with each other, like if they just kind of like crossed over and then all of a sudden the vertical line would hit them twice, but that doesn't happen. So no matter where we draw these vertical lines, we do only hit 1 point at a time, meaning that every input value produces exactly one output value as we go around this function. So this one is a function. Now, if we look at this next one, we have x equals y squared. So this is something that is a parabola, but it's not y equals x squared. It's the other way around. So when we plug in different y values, we can get out the x's. So like when y is 1, x is 1. When y is 0, x is 0. And then when y is 2, x is 4. So that's going to be like right there. But notice when y is negative 1, x is 1. When y is negative 2, x is 4. So we're going to get kind of like a top half up here and a bottom half down here. And this one, I think it's pretty quick to see that you can draw a vertical line almost everywhere along this function, and you will hit 2 different points. So like, you know, for the sake of the easy example, when you input x equals 1, you get out a y of 1, and you get out a y of negative 1. So this one, because you have inputs with multiple outputs, this one is not a function. Now, if we look at the last one, y equals the square root of x. So we plug in a few different values. So we get 0, 0, 1, 1, 4, 2. This one, it's only got one branch on it, right? So it certainly does seem like we're not going to hit any repeat outputs on this one. And that's true. This one is a function. Now, I do want to look at these two together because notice that this one, if you took the square roots of both sides of this, you would get y equals the square root of x. But by taking that square root, you would end up getting plus or minus the square root of x. And the fact that this has a plus or minus, this is what's giving us these multiple outputs. This one is just y equals the square root of x. So it's only the top half of that curve. Okay, so they're the same curve, but again, this one is only the top half. This one has a top and bottom half, which is why we get a difference between these two. So even though they both represent similar things, this first one in this form is not a function, and this second one is a function. Okay, so the way that we write them, the way that we set them up can change what that answer will be. Now, into more kind of formulaic territory, what we're kind of typically used to seeing in algebra. Standard notation for a function. This is written as y equals f of x, where x, the input, is the independent variable, and y, the output, is the dependent variable. So we say that x is independent because this is the input. You can put anything into the function from the domain. And the output, the y value, gets determined based off of what you put in. Okay, so like with this example we did back on the first page, I put in this input, it resulted in this output. I put in this input, it resulted in this output. My choice of what to put in was independent. What came out of it was dependent. Okay, it depended entirely on what was put in the first place. So in this notation, when we say y equals f of x, that does mean that y and f of x represent the same thing. So y and f of x are the same thing. We can use those interchangeably. A lot of times we like to keep the function notation, the f of x, because it allows us to see more clearly what the input is that's going into the function. But these do both represent the same thing. So let's try an example. So we are given two functions, f of x and g of x. And, excuse me, we have a few values to find. So we want to find f of 5, g of 5, f of 0, g of negative 2, g of a, and f of a plus 3. So with the numerical values, it's pretty straightforward. So for f of 5, we're going to take this function, this formula, okay, this rule, and instead of x, we're going to put in 5. So we get 4 times 5 minus 1. That's 20 minus 1 is 19. Okay. Then we get g of 5. And we can do the same thing. So just replace x with 5. So that's 25 plus 2 is 27. We can try f of 0. That's 4 times 0 minus 1. So that's negative 1. G of negative 2. So we'll plug in negative 2 squared plus 2. That becomes a 4 plus 2 is 6. Now for the little more abstract ones with a and a plus 3. The reason we introduce this notation here is because we don't want to only think about what happens when we plug numbers in to these functions. A, in this case, it can represent a number, okay? But This gives us the ability to look at a pattern for multiple numbers rather than just always plugging in one number at a time. So for g of a, we're taking g of x, but instead of x, we're putting in a. So that's going to be a squared plus 2, and I'll just drop the parentheses. So a squared plus 2, like that. And there's nothing more that we need to do with that. Okay, this is the formula now with a in place of x. And again, a could represent any number, okay, or any, other formula or, whatnot. But we don't just have to plug in like single numbers into a function. We can plug in other expressions. So like for f of a plus 3, it's the same idea. We're taking f of x, but instead of x, we're using a plus 3. And that's the entire quantity a plus 3. So we get 4 times a plus 3 minus 1. So let's distribute that. We get 4a plus 12 minus 1. So 4a plus 11. So that's going to be our result. Now, the next thing that we're going to be talking about, because this is a business calculus class, calculus for the social sciences, all that kind of stuff, we are going to be looking at applications throughout the semester. We're going to be looking at the idea of mathematical modeling. So mathematical modeling is basically just answering a real-world question using math, using like formulas, using functions, using algebra and calculus. So in essence, it's kind of like what you would call like a word problem. But these are problems that have real-world context that we can solve using our tools of mathematics. So, for example, if it takes someone t minutes to run a mile, then their average speed, s in miles per hour, is given by this formula, s of t equals 60 over t, for t greater than 0. Find s of 10 and s of 8, and then explain what those mean. So let's get s of 10 first. So we're going to plug in 10 for the t. 60 over 10 simplifies to 6. So let's think about what what all these are in here. 10 is the t value, right? So that's going to be in minutes. And s is going to be in miles per hour. And that's the value we just got for s. Okay, so our input of 10 produced an output of 6. So we can say when they take 10 minutes to run a mile, their speed is 6 miles per hour. So we input 10 minutes that it takes them to run the mile, and we output the 6 miles per hour, which is their speed. So we do the same thing for s of 8. So we get 60 over 8, which works out to 7.5. And it's a very similar interpretation. So we input 8 minutes, we output 7.5 miles per hour. So when they take 8 minutes to run a mile. Their speed is 7.5 miles per hour. Okay, so I think word problems get kind of a bad rap in mathematics. People are more afraid of them just because there is a certain level of interpretation that is required. But if you look at the level of the math that we did, all we did was we substituted in the number 10 and the number 8 into a formula that we were given and then got out those two numbers. The most important thing with these problems is that interpretation. So labeling variables clearly and being able to kind of explain verbally what those numbers mean in the context of those problems. So we're going to take a look at one more. A painting is purchased as an investment for $125. If its value increases continuously so that it doubles every 5 years, then its value is given by this function v of t, which is 125 times 2 to the t over 5 power for t greater than or equal to 0, where t is the number of years since the painting was purchased, and v is its value in dollars at time t. Find v of 5 and v of 10 and explain what those mean. So let's do the calculation first. So we need v of 5, v of 10, and explain. So we're going to use our formula here. So v of 5, that's 125 times 2 to the 5 over 5. That's 125 times 2 to the first, so just times 2. 125 times 2 is 250. So let's think again about what these mean. Our input here is a t value, it's a time, and t is number of years. And our output, v, which is going to be 250, v represents the value in dollars. So we can say after 5 years, the painting is worth $250, which if you think about it, it started off being worth 125 and it doubles every 5 years. So double of 125 is 250, right? So it's the same argument. And we do the same thing for v of 10. So that's 125 times 2 to the 10 over 5. So 125 times 2 squared. 2 squared is 4. 125 times 4 is 500. Which again, another 5 years passed and it doubled again in value. So we draw a similar conclusion. So after 10 years, the painting is worth $500. All right. And that brings us to the end of section 1.1. This is our kind of introduction into functions. When we come back with section 1.2, we're going to be looking at some more things we can do with functions algebraically. We're going to dive a little bit deeper into all that stuff, look at a little bit more application, and then just continue on our kind of review sections up here before we get into our new calculus material. So I will talk with you all in the next section.